Good afternoon, everyone. I hope everybody's doing okay today. We're going to be finishing off part one of the rest of the story today by looking at lesson 30.07, which deals with the double angle identities. Before we get started, I just want to say a few things about my perception of how things are going so far. Yesterday in the Google Hangout or Google Meet, whatever you'd like to call it, nobody showed up, and I'm totally fine with that if nobody has any questions. And although I have pared down the content considerably, I'm a little surprised that nobody would have questions. So I'm starting to get a little concerned about everybody's participation here, and I hope that you're still participating. I know that you're handing in assignments, but I'm curious to know if you're participating on a day-to-day basis. So before we get started with the second part of the rest of the story, which I will have prepared for you by next week, I'm going to be sending each of you an email asking you for some feedback on how things are and how things have been going so far with this whole online learning thing. I thought of potentially, sending out a Google form for people to fill out, but I think this would be more personal, and I would rather hear from you individually rather than you type some stuff into a form. So expect an email from me probably by the end of this week or early next week, just checking in on you. And I'm going to require that everybody reply to the email with a little story about how things are going so far. All right, let's get started. This is a fairly short lesson. If you followed along yesterday with the basic idea behind using identities, we're going to be doing the same thing today, except yesterday we were dealing with sum and difference identities for sine and cosine. Today we are dealing with double angle identities. And yesterday I talked about the fact that there are sum and difference identities for tangent, and we would normally study them, but I've chosen to throw them over the boards in our modified course. And I'm doing the same thing with the double angle identities. So there is a double angle identity for sine. There are three different double angle identities for cosine. And there is a double angle identity for tangent, but we're not going to be studying it. Again, I think it's important that you understand what's going on in these identities. If I asked you to determine what the sine of 20 degrees was, that's a pretty trivial matter for you to put it into your calculator. But what the double angle identity for sine says is since 20 degrees is 2 times 10 degrees, this is exactly the same as taking 2 times sine of 10 degrees times cos of 10 degrees. That's what this identity says. It says sine of 2 times an angle equals 2 times sine of the angle times cosine of the angle. And you can certainly feel free to check that on your calculator by entering sine of 20 degrees and 2 sine of 10 cos of 10 degrees and see that you get the same thing. With the cosine, I don't want to get into here in video form why there's three of them, but there are three of them. One of these identities identifies the value of cos of 2 times an angle using cosine and sine. One identifies the value of cos of 2 times an angle by using only cosine and the number 1, and the other one uses sine along with the number 1. It's very important that you don't confuse this identity where cos of 2 theta equals cos squared of theta minus sine squared of theta. You don't confuse that identity with the Pythagorean identity, which says sine squared of theta plus cos squared of theta equals 1. This is something different. You might wonder why we're worried about having three different ways to express cos of 2 theta. I don't know that we will run into examples where this is the case, but sometimes it's better to write cos of 2 theta as cos squared minus sine squared, and sometimes it's better to write it as 2 cos squared minus 1, and sometimes it's better to write it as 1 minus 2 sine squared. Certainly my calculus students, we will run into that sooner or later in calculus, that you have a decision to make. Which of those three identities will make your job easier in the problem that you're working on. So let's get right to the examples. You should have your formula sheet in front of you. And this is very similar to what we were doing yesterday. You are matching up a pattern with an identity to see which identity can be used in the question. So for example, in this one, I'm going to rewrite it. You have 2 times sine of an angle, which is 15 degrees, multiplied by cosine of an angle, which is 15 degrees. And we also have an identity that says 2 sine alpha cosine alpha equals sine of 2 alpha. So when we compare these two statements, when we compare the question to the identity, it becomes fairly obvious that what's going on here is alpha is 15 degrees. Right? Instead of having sine alpha cos alpha times 2, it's sine 15 cos 15 times 2. And that means that the alpha is 15, so this identity tells us that 2 sine 15 cos 15 is sine of 2 multiplied by 15 degrees, which gives us sine of 30 degrees. Now we're asked to verify the results on a calculator. By the way, you should know that sine of 30 degrees is exactly 1/2 from the unit circle. But let's go ahead and use the calculator. All right, am I in degree mode? I am, so I'm going to take sine of 30 degrees. Again, you should know that this is 1/2 or 0.5. Now what we want to do is see if it's equal to 2 sine 15 cos 15. 2 times sine 15 degrees times cosine 15 degrees gives us 0.5. So we're just verifying that it works. In other words, 2 sine 15 cos 15 is exactly the same as sine of 30. These two things are equal. Take a look at example B. What you're trying to do here is find an identity that matches that pattern. Well, there is an identity that has 1 minus 2 sine squared of an angle in it. 1 minus 2 sine squared of theta, when you go to your formula sheet, is equal to cosine of 2 times theta. And you might notice that I'm kind of switching back and forth between using alpha and using theta. I could use x, it really doesn't matter. Cosine of 2 times an angle is 1 minus 2 sine squared of the angle. So what is the angle here? This 20 is the angle that is in here. It's 1 minus 2 sine squared, not of theta, but it's 1 minus 2 sine squared of 20. Well, if that's equal to cos of 2 theta, and 20 is theta, then this equals cosine of 2 multiplied by 20, which is cosine of 40. And by the way, that 20 and that 40 are radians. There's no degree symbol there. So we can check this out on the calculator now by entering 1 minus 2 sine squared of 20 rads and entering cosine of 40 rads and seeing what we get. I'll do the cosine of 40 rads first. I want to make sure I'm in radians because, again, there's no degree symbol. So if I take cos of 40 rads, I get this number. Now I want to take 1 minus 2 sine squared of 20. 1 minus 2 times, now don't forget sine squared of 20 means sine of 20 quantity squared. But my calculator is smart enough when I enter sine brackets 20 n brackets squared, my calculator locks that 20 to the sine and takes the sine of it before it squares it, which is what I want. Anyway, when I hit equals, I get the exact same number. And you wouldn't verify these in the regular course of your work. We're verifying them just to show you that they are equal. We have one more example to do, question 2. As I said, it's a pretty short lesson. We have angle A in quadrant 3, and tangent of the angle is 5/14. I hope you're starting to recognize this. This happens very frequently. You're dealing with a quadrant 3 rotation angle, and you're given a tangent. And the reason why that information is significant is because when we start to talk about x, y, and r, quadrant 3 endpoints on a rotation arm have negative values for x and y. We'll just shelve that away for a second and look at what the question is asking us. What's the exact value of sine of 2 times the angle? Well, we have an identity for sine of 2 times angle A. It's going to be equal to 2 sine of A cosine of A. That's the double angle identity for sine. Well, sine of A will be y over r. This is very similar to what we did yesterday. Cosine of A will be x over r. In fact, everybody, and then we have the 2 here. What we did yesterday was more complicated than this, because what we did yesterday, there was an angle A and there was an angle B, and we had to make sure that we knew which x, y, and r we were referring to when we calculated the sine or the cosine. Here we don't have to do that because they are all of angle A. Don't forget, up here you're told tangent of angle A is 5/14. Don't forget that tangent is y over x. So that means that y would be -5 and x would be -14. And from that, we can determine the value of r. We're going to use the Pythagorean theorem, x squared plus y squared equals r squared. So we're going to have x, which is -14 quantity squared, plus y, which is -5 quantity squared, equals r squared. Something tells me that that's not going to be a perfect square, but we'd better work it out. -14 quantity squared plus -5 quantity squared. It's very important that you put the negative in the brackets because you have to square the negative. Many of you might just not put the negative in because you know it's going to become positive when you square it, and that's fine. I get 221 for r squared. And 221 is not a perfect square, which means that r equals the principal square root of 221. Well, we're just about done here. R is equal to root 221. What's inside of this rectangle is important to solving the problem, because sine of 2 times A will be equal to 2 sine A cos A. And as we said, sine of A is y over r, so that's -5 over root 221 multiplied by cosine of angle A, which is x over r, and that gives us -14 over root 221. And now what we can do is simplify that by multiplying across the top and multiplying across the bottom. 2 times -5 times -14 is going to give us 140 over, when I multiply across the bottom, we have root 221 times root 221, which is 221. Now, I want to address something just briefly here, because some of the students in this course will end up being confused about our answer. You were told that angle A is in quadrant 3. And that's why when we had x, y, and r, we had made a decision that x was negative and y is negative. And what's going to happen is some of the students are going to look at this and go, wait a minute, this is the sine, right? This is the sine of 2a. And then they're going to go over and they're going to think about quadrant 3 and they're going to eyeball the fact that y is negative in quadrant 3. And they're going to be confused. And I've even had students on an exam second guess themselves and say, well, it must be negative 140 over 221. I must have made a mistake someplace. And no, we didn't make a mistake. The answer is positive 140 over 221. Just because rotation angle A is in quadrant 3 doesn't mean 2 times rotation angle A is in quadrant 3. Just to give you a quick illustration of this, if we had a rotation angle, theta, of 190 degrees, well, 190 degrees is definitely in quadrant 3. It's 10 degrees below the x-axis. So theta equals 190 degrees. Well, what does 2 theta equal? 2 theta equals 2 times 190, which is 380 degrees. And if you were to track where 380 degrees comes out, it comes out over here in quadrant 1, where sine is positive. So just because theta has a negative sign doesn't mean 2 theta will have a negative sign. So that is the answer to the question, 140 over 221. We take a look at the second part of question 2. You're asked for cosine of 2 times a. Don't forget, for angle A, we had x equals negative 14, y equals negative 5, and r equals root 221. Now, how can we find out what cosine of 2a is? Well, cosine of 2a is equal to cosine squared of a minus sine squared of a. That is one way that we could find cos of 2a, because the double angle identity for cos says cos of 2a is cos squared minus sine squared. Well, let's try that. We're going to have to take cosine of a, which would be x over r, which is negative 14 over root 221. We're going to have to square that and then subtract the square of the sine. Sine is y over r. Let's see what we get. When I square a fraction, I have to square the numerator. Negative 14 squared is 196. Over, when I square the denominator, the square root and the squared eliminate each other because those are inverse operations. We get 221. And then we have minus negative 5 quantity squared is 25 over root 221 squared is 221. Okay. Well, we have a common denominator, so we can piece these two fractions together and say the answer is 196 minus 25 over 221, and that gives me 171 over 221. And that's the answer to the question. Now, what would have happened had we used the following identity? Cosine of 2a equals 1 minus 2 sine squared of a. Let's see what happens. We get 1 minus 2. Well, what is sine squared of a? It's the y coordinate over the r value quantity squared. So we're going to get 1 minus 2 times the square of the sine, which will be 25 over 221. When I take 2 times 25 over 221, I get 50 over 221. And I won't bore you with the details here, but you could either find a common denominator or use your calculator. What this is going to equal is 171 over 221. And if you use the third version of the double angle identity for cosine, which is cos of 2 theta equals 2 sine squared theta minus 1, you would still get 171 over 221. So very short lesson. It's about recognizing those double angle identities and where you can use them. And then it's also about going back and applying your knowledge of x, y, and r with these identities just like you did with the sum and difference identities yesterday. So your assignment is on page 306, do number 4 all, and do number 20 all as well. I know in your handout I said just do C and D, but do them all. As well, complete question 1 on the page after this lesson in your handout. So I hope that made sense, and I hope you have a wonderful rest of the day. And if you have any questions, please reach out to me so that I can help you out. Tomorrow, which is Thursday, we are having another Google Hangout. If you have problems, please show up. And if you don't want to show up, you're not comfortable, please send me an email letting me know how I can help you. Have a great rest of the day, you guys. We'll talk to you soon.